cool them, they contract. So this expansion and cooling, it can cause cracking in the fuel cell. That's kind of the biggest problem in this technology. So we have stability issues. Materials are poison, they are very sensitive to certain elements. Sulfur, which is sometimes in fuels, there are certain fuels, they have sulfur in it, and that can poison our anode. Carbon is also one problem. If we supply carbon, let's say methane or any other hydrocarbon at the anode, this poking problems, which means carbon formation on the anode side, is a big issue in solid oxide fuels. And Shirley is also working on that one for her doctoral thesis. So that's one big problem. And another thing is like it has very long startup times, and these systems are very expensive. So these are the problems. The main idea of showing this slide is to show that this high temperature is something which is an issue, and we would like to decrease its operating temperature. That's the main thing. But at the same time, we want to decrease the operating temperature of the device, but we don't want to lose any performance, because these devices give, let's say, 1 watt per square centimeter at 800 degrees, but we would like to get the same performance at lower temperatures. And when I say low temperatures, I mean something between 400 to 600. It's already a progress from 800 to that. Ideally, if it would work at room temperature, that would be great. But the problem is like we don't get enough ion conductivity, so we need to raise some temperatures. But 400 to 600 is already quite good. So, okay, one question. So basically, I talked about the solid oxide fuel cell, and I also briefly talked about other fuel cell technologies. And I said one thing during my talk, that what is the main advantage of using solid oxide fuel cell over PEM fuel cells, which are the low temperature fuel cells. And I write here 3 options. Because solid oxide fuel cells are low cost, they are excellent for mobile application, or fuel flexibility, that we can apply different fuels. What do you think? Which of these options? I think everybody knows, but they are shy to answer. Yes. Or should you can tell?
Yeah, I think it's the last one.
The last one, yeah. I think everybody knows about it. I think that was pretty straightforward. Yeah, exactly. So that was the main idea. Yeah. I didn't talk about any thing about mobility or application. I should have talked about the applications also, but I was thinking that maybe that's not very interesting for this one. Okay, and then I'd like to also briefly cover, we talk about those electrode properties and ionic conduction, but I'd like to just like to ask you, when we are choosing materials for our electrode, what kind of properties we would like to have in them, properties. So what kind of properties you want? They have to conduct, or so any guesses what kind of properties we want in electrodes? So I put 5, so let's see. So basically our electrodes, they should conduct electrons, or yeah. So they should have good electrical conductivity. Okay, that's one. And anything else coming in your mind?
Pores.
Yeah, they should be porous. Yeah, so that the gases can diffuse through it, and they should allow electrons to connect. Please.
Mechanical stability?
Yeah, exactly. That's very important. Mechanical stability, because we have to use them at high temperature, and yeah, exactly. Yeah, mechanical stability.
High surface, like.
The surface area, exactly. But we have good porous structure so that we get high surface area. Yeah, that's correct. Anything else you like to say? Okay, that's actually very good. Excellent. So basically here I put like my own list of, they should have good electrical conductivity so that they can conduct electrons. They should have good catalytic properties. They should be good catalysis. And then the thermal expansion coefficient, it should be matching with the other materials, because if the thermal expansion coefficient is not matching and we operate the device at high temperature, there is thermal mismatch and it can lead to cracking or this kind of issues. So this is also one issue that we need to take into account. Chemical stability, they should not chemically reacting with our electrolyte and like create problems. But how about this ionic conductivity? How about if our electrode materials, they also have some ionic conductivity? So is it a good thing or is it a bad thing? What do you think? You are saying something?
Yeah, it's a good thing to
Isn't it?
increase the three-phase boundary.
Yeah, exactly. So if our electrode materials also have this ionic conductivity, which means they have good electronic conductivity, but they have also, if they have good ionic conductivity and electronic conductivity at the same time, then it's a good thing, because then the reaction can happen at larger surface, and we have increased triple phase boundary. Exactly. So these are the things. But excellent. Great. Okay, so the same thing in balloons. I think we have covered this.
Yes, yeah. So, greetings from VTT. I'm working with fuel cells. I'm here for interest, and maybe see you in 2 weeks when I can come here to talk. But just a question about the electrodes. So, some question that I sometimes get from students or visitors, that these are quite exotic materials, sometimes lanthanum, strontium, langanite, cobaltite, and can you give some comment? Maybe you have more new information that how is the availability and the amounts are really small, but in the long term and mass production, could you say that it's rare?
Unfortunately, no. Generally, we just buy from the things, but I know these elements are quite. They are not like plenty in nature, so these are issues.
Yeah, but the positive is of course that the amount of them has been reduced.
Yes.
Very, like, I would say even dramatically.
Yeah, true.
What it used to be 20 years, 10 years ago.
Exactly.
It's pretty small now, And they are really good in the catalytic activity.
Okay. So this is our first part of our talk. And then now I go more into what kind of research we do in our research group. Because these are kind of next generations of solid oxide fuels. And as we know so far in the lecture, that solid oxide fuels is a promising technology. However, the ionic conductivity is a big issue, and we have to operate at high temperature. Now our research efforts mainly are on to decrease the operating temperature of this device, but at the same time not compromising on the performance of the cell. So this is the main thing. So let's start with the ceramic nanocomposite fuel cells. Ceramic is like metal oxides. They are like solid oxide fuel cells. Solid oxide fuel cells are also called ceramic fuel cells. But here I added this nanocomposite word there, which is like, even in solid oxide fuel cells we have nanocomposite materials in a way, or electrodes, they are nanomaterials. But here I need something different, and I will explain here. So, starting from here, as we know, the performance of electrolyte zirconia is limited by ionic conductivity is limited below 600, even below 800. At 800 it's 0.1 Siemens per centimeter, but below 600 it's very, very low. So it's not possible to use it. And in our NHS we have the equation for resistance. So if we want to decrease the resistance of this electrolyte layer, because when we have low ionic conductivity, we suffer from high ohmic losses in the electrolyte layer. And if we want to decrease the resistive losses there, we have two possibilities. One possibility is to decrease the electrolyte layer thickness. If we have thick layer, then we have more losses, but we can make it thin. But there's a limit. If we make it too thin, then the gases can cross over, and that's also we don't want. So it has to have certain thickness, but it has to be very dense so that it doesn't allow gas to pass through it. And the second way to improve or decrease this resistive losses is improve its ionic conductivity. And in our group, we are mainly focusing on improving its ionic conductivity. So what we do is we use a composite material. We mix this solid oxide fuel electrolyte material with some alkali carbonates. We generally use this lithium, sodium, and potassium, which have different melting temperatures. So this is the eutectic temperature of these three carbonates: lithium carbonate, sodium carbonate, and potassium carbonate. When they are mixed in this mole percent ratio, we get the melting temperature of this can be 397. When they are alone, like lithium carbonate has 723, sodium. So these are the melting temperatures of those carbonates. But when we mix them, their melting temperature goes down. So if you see the phase diagram of those, which is not the main topic of this lecture, so we can, making different composites, we can decrease the melting temperature of the mixture. And eutectic temperature is the point where it has a minimum melting point. So when we mix them in this mixture, this is the lowest melting point. So the main idea is that if we mix our heterostabilized zirconia or any ionic conductor, gadolinium, dopsilia, or there are some other ionic conductors, if we dope or if we mix them with this alkali carbonates, let's say with this composition, at 400 degrees and over, it melts. And what we see is that it improves the ionic conductivity. So generally, we see in case of solid oxide fusel materials, there's a straight line in the INS plot. But here we see some kind of a jump over, for example, in this case, over 400, we see there is a jump here. And we notice here that when we increase this carbonate content, when we increase, for example, in this case, we have pure SDC, samarium dopsilia, which is like this here. But when we add 10% of carbonates, so it's 90% of ionic conductor, like solid oxide ionic conductor, and 10% carbonates. So ionic conductivity improve in this temperature range. When we increase carbonate content, it increases even more. And then this is in case of 50%. So in this case, we have 50% carbonates, 50% samarium dopsilia, and we improve its ionic conductivity. So basically what we noticed is when we mix conventional solid oxide fuels and electrolyte materials with alkali carbonates, we see some improvement in the ionic conductivity. How it happens, that's another thing, but that's what we noticed. And that gives us a hope that using those mixtures, we can reduce the operating temperature of these devices from 400 to 600. So that's what we are trying to see. So these nanocomposite materials, so I'm calling these nanocomposite materials, which means they are composites of this samarium dopsilia, like cerium oxide, which are ceramic materials, with the alkali carbonates. So these are nanocomposite materials, and they can give high performance at low temperature. And that's what we are mainly focusing on in our research group. Okay, so now try to see how these composite fuel cells work, because they are more complicated than solid oxide fuel cells, where everything is kind of more clear. We have only one oxygen ion which is moving through in the electrolyte layer. But this is a bit complicated device. So in this case, we have, okay, this is a schematic structure of ceramic carbonate nanocomposite fuel cells. And we have these composite materials here. We supply hydrogen here, and here we supply oxygen, but we can also supply carbon dioxide here. It's kind of a mixture of molten carbonate fuel cell and solid oxide fuel cell. That's how generally I see it. So we supply these gases here, and we get all of this kind of ions. It generates hydrogen ion, and it exhibits basically this multi-ionic conductions. We generate this alkaline ions, we get oxygen ions, and carbonate ions, and so we get different kind of reactions happens, and we don't understand exactly how these reactions are happening. So we have different, we assume that it's acting as a solid oxide fuel cell and it's an oxygen ion, but we also see that when we operate it over the eutectic temperature, the performance increase. So what is supporting this ionic conduction in the electrolyte layer? It must be some other ions. So that's what we all think about, and I will show in later slides our hypothesis about it. But in this schematics, we just assume, okay, we have carbonate ion conduction in the electrolyte, we have oxygen ion conduction, we have hydrogen ion conduction, hydroxide, and lithium and sodium, or if we have even potassium, then even potassium ion, they will also conduct in the electrolyte layer. So we have this multiple ionic conduction. But which ion is dominant in the ionic conduction, that's a question mark. And for that we do this ion transport measurements, try to see which ions are dominating the ionic conductivity here. But that's more complicated and we don't understand it that thoroughly. But here are some proposed reactions, possible reactions that happens on the electrodes. For example, when we supply carbon dioxide and oxygen at cathode, they get electrons, they reduce, and they give carbonate ions. And these carbonate ions move from cathode to anode, and at anode it reacts with hydrogen gas, and it gives us water and carbon dioxide, and we get electrons. So this is one possible reaction scheme, that we get hydrogen, oxygen, carbon dioxide, and we get water, but in this case carbon dioxide also. The other reaction scheme is like we have a hydrogen ion and we have this alkali carbonates, metal carbonates, lithium carbonate, potassium carbonate, or sodium carbonates. They react, and as a result we get these metal ions, alkali ions or sodium ions, even potassium ions, and they move from anode to cathode. And we get electrons, but when they reach at cathode, they get these two electrons and become metal carbonates again. And overall cell reaction will be like this one. So in this scheme we are assuming that this ionic conduction is taking place through alkali ions, and in this case we are assuming that it's happening through carbonate ions. So both are possible, but we do not know exactly which reaction scheme is dominating unless we apply some analysis and characterization technique and try to dig it more. But the best thing is we get higher performance at lower temperature, and we will see it soon. Okay, one more thing here. Since it's a composite material, the blue color over here that you see, it's basically the carbonates. And as I said, over the eutectic temperature, which is over 400 degrees, this carbonate is in molten form, liquid form. So here I show it with the blue color. And these white dots that you see here, these are our metal oxides, like ceramic material, a gadolinium cerium oxide, or any ionic conductor which is metal oxides. So now the ions move through different channels. For example, the oxygen ions, they move through the vacancies in the bulk of this, like in case of solid oxide fuel cell, move through the bulk of these oxides. But now we have also carbonate ions which can just flow in the electrolyte, in the carbonate. They can go through this layer, or they can transport through the interface, or a combination of those. So there are different channels. And from the literature and from our experiments, it seems to us that these interfaces are very crucial for the ionic conduction here. So it means that we need to have an optimized composition to get higher performance. But this is just the overview of this. If you don't follow that, that's perfectly fine. But now here is what we do in our research group. We synthesize these nanomaterials, starting from these nanomaterials, and we do different synthesis methods for that. Then we characterize those nanomaterials, try to see whether we have gotten our desired properties in those nanomaterials. For that, we have different characterization techniques we will go through later on. And from those nanomaterials, we do device fabrication by different fabrication methods. And so there are different fabrication methods that we use for this device fabrication, and then we characterize. And I think in your lab sessions, you will see, I think, how to make fuel cells, and also you will do this characterization in the same lab, so you will get better idea of how they actually look like. Okay, but here we start with, the first step is to synthesize different nanocomposite materials, and there are different ways to prepare, there are different synthesis routes to prepare these nanomaterials. Without going into detail there, I just like to show just their names, that there are different ways available to prepare those nanomaterials. So we have this co-precipitation method, some reaction scheme. Okay, we don't go in detail in this lecture. There's a Solgen method to prepare these nanopowders, and then we have this freeze drying method to prepare these powder materials. And the freeze dryer, they actually look like this. It's a machine that you will also see in the lab. And here is the reaction scheme. And I think that we can skip. And the main idea is that by using those precursors and their compositions, we can get these nanopowders in the desired composition and with the desired properties and particle size and all those things. Okay, that part I skipped. Just wanted to show you. So once we get these powders, the next step is, okay, we synthesize all different kinds of nanopowders. The first thing is we want to get the right composition. For example, if we have alkali carbonates, eutectic mixture of alkali carbonates, then we have our ionic, this electrolyte material, metal oxides, ceramic metal oxides. In electrodes, we also use composite materials. So we do all those kind of mixing using this ball milling machine. So we put our powders in those jars with the balls, mix them. We can also reduce the size of the particles also by milling them, but generally we use it for mixing. The powders we purchase, they are already in the right size. Then we dry them because we use some kind of solvents in those ball milling machine. So we get this powders which is dry now, and then we grind it, and then after those compositions are ready, we start making our cells, which we also call pellets, which look like buttons. So we take a small die, we weigh the powders, we place the powders in those dies, and then we bring in this press machine. We place our die here, our powder is in some kind of a container or some die, and then we press the powder, and we get some pellets. But those are quite fragile, and then we need to sinter them so that all the impurities, or if there is any binder that we use to bind the particles together and to improve the interface between the particles, we do sintering. After that, we get some buttons. I should have one figure of a pellet here, then it's more clear. So we have these powders which look like a button now, and then we apply some gold electrodes, and then the cells are ready for electrochemical characterization. Okay, here is like much more clear. So this is how a fuel cell in our lab look like. This is like a button or pellet or what you call it. So powder, when we place it in this press machine and we press it, it will look like this. And then the next step is to characterize it. And in our lab we have 3 different fuel cell setups, and here is one of those. It's a probostat. Here we can see it better. So we apply these current collectors on both sides, and there is a this gas tube here. Gas is coming here, and this cell is placed on top of this tube. So the lower surface of this cell is exposed to the gas in this tube. And then we have another gas coming to the external part of it. So the outer surface is exposed to one gas, and the inner surface is exposed to the other side. And this is how it looks like. When we place our cell on top of this tube, this is how it looks like. And it's very important to seal it very well. Otherwise, the gases from the inner tube can go to the outside. So we have to seal it very well. And then we apply these current collectors, inner side, outer side, and that's it. And then we apply the gas here. Just close it, the outer chamber, if they call, and then it's ready to be measured. And then we have a furnace, and all the electronic part is here. So we have the gold electrodes, and here we have all the electronics, which is outside the furnace, and the upper part where we have our cell is exposed to high temperature. So that's how we do it. And then we apply different kind of current voltage measurements and impedance measurements. We will go through it in more detail. Great. Okay, so that was about this. Okay, and then the first thing, if we are making electrolytes, we measure its ionic conductivity with the same Arrhenius plot that we have seen, and you also have one homework on that one. And here is one Arrhenius plot of a composite material. And as I said, there is a straight line here, but around, this is I think around 400 or 500. This is the binary carbonate, so it's 500. The ionic conductivity jump rapidly. So something happens at this point, and then at some point it starts increasing linearly again in the logarithmic scale. So